webinar series. Before we get started, I'd like to go over a few housekeeping items. First, all the boxes that you see on your screen are resizable and movable, so feel free to move and expand those as needed. We will be answering questions live near the end of the session, but feel free to submit your questions at any time using the Q&A widget. A copy of today's slide deck and additional help materials are available in the resource list. We encourage you to register for the complete series if you've not already done so, using the link in your resource list. Today's webinar will be available on demand should you wish to revisit after the session or share with a colleague. If you are experiencing technical issues, please refer to the help widget or submit a question to the technical support widget so we can assist you. Additionally, you may be interested in our Digital Enterprise Virtual Roadshow, which is a series of webinar and panel discussions about the challenges and benefits of digital transformation for your utilities and other asset-intensive industries. Separate registration is required for this series. You can use the link in your resource center to register. With that, I'm proud to welcome today's presenter, Hitachi ABB Power Grids Canada Regional Technical Manager, Jack Chang. Jack?
Thank you, Sarah. Thank you, everybody, for attending. The topic for today's webinar is busbar protection fundamentals. So the agenda today is to first introduce different types of bus configurations that you commonly see in high voltage, medium voltage substation, and different types of bus protection schemes. We'll go into details, introducing, highlighting the pros and cons of different schemes. And then we will highlight, and finally we'll highlight, I'll introduce and explain, list the different features for modern numerical bus protections. And then last but not the least would be a question and answer sessions that I will try my best to answer your questions. So you can always send me an email or contact me directly if you have any follow-up questions as well. The objectives for today's webinar first is to identify the reasons and requirements for busbar protections. Second is to identify the common busbar configurations and understand their protection requirements. And the third is to identify common issues faced by busbar protection to assist engineers in their design of busbar protection scheme. Last but not the least is to understand the principles, pros and cons of different busbar protections. So first, what is the busbar protection? Okay, so because in the high voltage digital substation, there are different types of busbar configurations, layouts, and designs. They are designed to facilitate, operational flexibility, maintenance, and reliability. So that's why there are different busbar protection schemes that's suitable for certain busbar designs and not another, and there are challenges and requirements needed to caters to different bus configurations. And complexity of those protection schemes also varies. The different type of busbar designs include such as AIS, air insulated, GIS, gas insulated, the IPBD, isophase bus duct, that's usually seen in power plants, and also cables sometimes are used as a busbar in the station just to connect to rigid, for example, bus structure as well. And all those segments of the busbar need to be protected properly. Busbar fault. Faults on busbar is infrequent. It doesn't happen very often because it's actually located inside the fence, inside the fence of a substation. But however, it's usually seen. Usually when it happens, usually it's very robust with very high current levels. So any delayed clearance of the busbar, especially when it's close to a strategic generation asset, it could lead to network instability, cold slip of large generators. So that's why fast clearance, especially on high voltage busbar substations, is mandatory. And protection need to be very defendable, need to be clear the fault in high speed, and need to be reliable as well. It must be stable for all external fault, because external fault on the busbar is much more common. Closing external fault could impose the maximum short circuit duty to simulate internal fault, so that in return that could cause heavy CT saturation. However, CT saturation basically can result in the differential current measurement by the busbar protection, and such saturation must not lead to misoperation. Therefore, the busbar protection scheme must be designed to be secure and selective, as any misoperations could lead to a disconnection of all connected elements. Busbar protection is easy to detect because of the robust natures. Most commonly detected using the differential principle, as we will introduce in this webinar. So the next couple of slides, we will introduce the different common busbar design, and we will have the poll questions at the end of the next few slides to get some ideas of what's the common busbar design that you commonly see. First, simple bus. Simple bus, basically, as its name suggests, it just consists of a very simple a single bus bar where all the elements or assets, operators, are connected to it. These flexible. Any CB maintenance, if you want to maintain the CB, maintain the circuit breaker or the disconnect associated to those circuit breaker, you need to basically interrupt the circuit that's serviced by the circuit breaker. No switching is required, basically, in terms of the protections. And then each 87B, the busbar protection, busbar differential protection, either is a physical device or an element in the modern IED. Is intelligent electronic devices, can protect one bus bar. You can basically use modern IED if you have multiple 87 elements, you can protect multiple simple bus bar that way. But traditionally, conventionally, each bus bar would be assigned to one physical protective relay. The second is the main and transfer bus. This you probably don't see very often in North America, but that's a common way where you will have a transfer bus where you enable some flexibility to take certain elements out of service. For example, you want to take a breaker out of service, then what you can do is actually you can close the transfer breaker, the tie breaker, and then you can close the tie, and then you open up breakers. However, with this kind of bus configurations, that would mean that provisions and logic need to be implemented to switch in the CT from the tie breaker bay, from the transfer bay for the protection of the bus. Because this tie breaker, when it's switched in, you need to be switched in to protect any of the three, in this example, any of the three circuits. So, that means certain kind of logic need to be implemented in the relays to support that. So any of these two CT need to be able to protect, logic need to be implemented to protect any of these three circuits. This type of switching logic conventionally was implemented realized with auxiliary relays before. But now it can be easily accomplished internally by IED programmable logic. Double bus single breaker, you commonly see this type of bus layouts in a very large switchgear lineups, typically in GIS, because it's compact, it took less space. It's supplied to a large number of feeders. So it's flexible. It can transfer and balance load to either bus. Okay, you can transfer all the load to one bus while you service the other bus. So on the other hand, in other words, these bus can be, one of these two buses can be actually used as a transfer bus, just like the previous scheme. Some type of dynamic zone switching must be in place because the bus protection need to know which currents or CTs, current transformers, which circuit is connected to which bus bar. And typically, you would know that by using the status of disconnect switches. There are certain requirements of performance requirements and timing that's required for these disconnect switches to properly indicate the connection, connected, disconnected status. And CT switching is required, and this typically is done modern relays by internal bus protection logic. We call that dynamic CT assignment, zone assignment. Breaker and half typically are seen in high voltage, extra high voltage transmission, and major power plant switching stations. It's quite popular in North America because it's extremely reliable. You can see that each link, if you count, each link is protected essentially by a 1.5 breaker, because you have two circuits, but they have 3 breakers. So each, you can say, you can do the math by dividing by the division, and it turns out that each circuit is basically provided by 1.5. The advantage of this is reliability. Any circuit breaker, any bus stop can be taken out of service for maintenance and without interrupting any load. Dedicated bus protection for each two of the main bus are required, and it can be achieved by using one single IED, bus protection IED, with 2 differential zones or with 2 separated physical devices. The bus stops here, these are called bus stops, are typically included in a connected apparatus zone, such as transformer, reactors, lines. So in this case, no dedicated bus protection is required. Rim bus is very similar to breaker and half, but typically are used in slightly lower voltage, such as sub-transmission or in maybe 138 kV class. The number of breakers and the number of circuits are the same here. You have the similar reliability benefit that any circuit breaker or bus stop section can be taken out of service without interrupting service to other circuits. However, care need to be paid that when load and source design consideration operation is equally important, because when you take one breaker, for example, out of service, you open one breaker, then you need to make sure that you have the correct or balanced source and load ratio, that when there's a second fault hit, you wouldn't lose the load. In other words, it's good that you have source and load that's actually adjacent to each other, instead of source on each side. You would like to have source and load adjacent to each bay, instead of all load on one side and source on the other. Usually no dedicated bus bar protection is needed, because all these bus stops can be provided by the apparatus protection, such as transformer lines and reactors. And the advantage of this is all protection zone can be made overlapped. And we will introduce the concept of overlapping protection and the advantage of that. Simple bus with coupler is commonly seen in medium voltage industrial or sometimes utility distribution stations. Each source transformer, typically each of this bus, the tiebreaker can be operated normally open, normally closed. If each of the bus segment are fed by a transformer, incoming transformer. The incoming transformer are typically rated to feed the entire bus section and feeding all the loads, both bus sections and loads. It can be done, the protection of that of the bus bar can be done either with the dedicated differential protections for each bus section, or through, we call it reverse blocking, or with partial differential. Partial differential means you typically would externally sum or internally sum the source CT from the transformer and the tie CT. That way you can isolate actually bus bar A from bus bar B. The bus bar transfer scheme can be designed so that you can automatically, operate and switch the tie breakers, the breakers and loads to the bus. Okay, let's take a quick poll for what we have just gone through about the different bus design and layout. What is the most common bus bar design that you have seen or experienced in the transmission station? Maybe not necessarily limited to transmission stations, but any substation that you have worked for. There is simple bus, breaker half, rim bus, or transfer bus. Are these the most common ones, or in your opinion, you have seen others? Share at the end of the webinar. We'll give it probably 20 seconds, and then we will progress to see the results. Okay, let's see how we do. So yes, as expected, green bus 20.5%, breaker and a half about 46%. Yeah, breaker and a half typically we have seen the most probably yes for high voltage stations, especially in North America. And transfer bus maybe not so much. Yeah, that's expected. Simple bus probably is used mainly for smaller stations. Thank you for your participation, and let's progress to the next section of this. So, what other considerations are needed for designing a busbar protection scheme? There are some issues there that are characteristic of the busbar protection. First is unavailability or availability of overlapping protection zone, and how they contribute to the issues. The issue here is for the lack of overlapping protection zone that will contribute to the so-called blind or end zones. How do you address that? Will load and source be switched from one bus to the other, such as the double bus bar single breaker scheme that I introduced earlier? You sometimes depending on how many feeders, some feeders will be connected, assigned to bus A, the other one to bus B. So you will need to know the bus protection differentials. Actually, need to know if the differential protection will need to know which feeders are connected to which zones. Following the same concept for number 2, the current transformer need to be switched from one zone to another, or are they shared? Open circuit conditions, open circuit of this current transformer, open circuit of any transformer apparent obviously will introduce undesirable differential current, and how do you cope with that? And then CT saturation. Modern busbar protection typically has a mean to detect CT saturation and then cope with that to block the adverse effect of a CT saturation to avoid any misoperations. We will look into these issues the next couple slides. First is CT location and zone of protections. So ideally, you would like to have overlapping CT across every breaker. And typically for dead tank breakers, you typically have CTs, groups of CT cores on each side, and you can achieve this, this type of overlapping without any issues. My understanding is in North America, especially in the United States, dead tank breaker is probably the most popular breaking apparatus in the substation. Okay, but I reside in Canada. I support Canadian customers, so utilities. So what we have here mostly actually for high voltage station are light tank breaker that you see on the right hand side. For light tank breaker, you need a dedicated freestanding CT. So because of the cost, you need a structure, you need a civil foundation, etc. You typically won't have CT on each side of the breaker like a dead tank. So you only have it on one side. Because of that, then you end up having a zone here, called that end zones. End zone could be a blind zone. Blind zone means it's under tripping by one protection, or over tripping by the other. So you can see here, if the fault hits in this we call it end zone, then what happened is for the green protections here, it could be a differential for a connected transformer, for example. Then you won't see this fault. So basically you won't operate on this fault. So you won't operate on this fault. The fault is still here. Okay. However, the blue zones actually will operate this fault. However, even the blue zone operated and opened this breaker, the fault is still there because the green zone would not be. The green zone does not operate to clear that fault. So this is what we call a blind zone for this green protection zone. So the solution for that, there is a solution for this. So the solution for that depends. It depends on the requirement, the performance of the protection requirement, the speed, essentially. You could wait until the breaker field protection operate typically in a 9 cycle, 12 cycles to take this fault apart by actually tripping adjacent breakers. Okay. However, in that way, yeah. And then the other solution, actually a faster solution, but it's more elegant but not commonly done, is if you realize that you have this situation, this problem, you could build this into your logic. When the breaker is open, okay, you take this CTs out of the connected differential relay. A modern software-based, modern IED platform, you can easily achieve that by doing that. Once you remove this protection when the breaker is open, you remove this CT to the connected protection scheme, the differential scheme, so you will operate. The green protection will operate right away. So when this breaker first open, the green zone will, by the blue protection scheme, the green protection scheme will open when you reach the CT connection removal I'm referring to is not physically, it's actually virtually through software. That's one elegant way to solve this. But mind you, people also comment that the likelihood of this happening right here, the fault happening right here, is very, very slim. That's correct. However, if this is the extra strategic, important extra high voltage stations, typically high voltage station, you will have freestanding CTs, a light 10 CT, a light 10 breaker. Then in that case, then yes, you probably don't want to wait. That depends on the studies, the stability studies to support this type of decision. Next is the different type of bus protection. We'll cover differential, the 4 different types of differential, the zone interlocking scheme, and the backup scheme. Differential principle, I believe everybody knows about that, is very familiar with this. There are 3 measuring conditions. Under normal load flow, there's no differential current. Okay, that has to be, if the circuit is connected, the CT circuit is connected correctly, polarity is connected correctly. Under normal load flow, no differential current. During external fault, ideally there should not be any differential current. The protection must be stable for external fault, especially your bus protection, because any operation you will actually take out the entire bus bar. During internal fault, there will be a high differential current, and that's where the protection need to activate, need to operate. However, during heavy external fault, CT saturation can cause very high differential current for external fault. Similarly, for internal fault, the CT can saturate and delay the operation, and all these need to be looked at by modern protection scheme. So the challenges are for the differential scheme, for a successful design of the differential scheme, bus differential scheme, is the different CT ratio and characteristic. This is not common anymore nowadays. Typically, when you design a bus protection scheme, the first priority is you want to make sure all the CT ratio for the connected circuit, connected base need to be the same, need to be equal. But in some very old stations, depending on the, probably because of the different age or vintage of the CTs, the CT doesn't support certain ratios, or because of the increase in fault level, you probably need to increase the CT ratio, but one CT doesn't support that ratio for some reasons. Then you need to match that ratio. Traditionally, you could use the series CT, externally connected with series CTs to match ratios. That's one way. Modern IED platform typically has different ways embedded to do this, usually software-based. Some vendors actually resorted to converting everything to the primary values, basically eliminating any secondary CT conversion effect. So you basically calculate the differential current in primary value. So basically there's no more CT ratio effect. That's one way. The other way is to use some kind of reference. Pick one CT as a reference and then convert every CT according with respect to that reference CT ratio to convert every actually CT secondary measurement to that reference CT. That's another way that you can compensate for. The other challenge is the large number of CTs, right? Because for a very large bus bar, we don't commonly see that in North America. In Europe, Asia, there's a bus bar with 30, 40 feeders, and modern numerical relays actually is limited by the number of connected CT circuit you can support, you can protect. So with such a large number of CTs, then really the only solution, either one is you divide that bus bar multiple segments, introducing breakers or these connectors, right, to divide that into smaller, manageable, protectable segments, or the other one is resort to so-called decentralized bus bar protection solutions technology. And then we have a couple slides to mention about that. And typically, decentralized solution will support the larger numbers of connected CT. And CT switching, in and out of zone, we mentioned this many times prior, that you need to, based on the disconnect status, you need to be able to, that the CT can be switched in and out of different protection zones. Okay. First is basically very simple, differentially connected overcurrent relay. Basically, it's overcurrent relay. However, you connect the external circuit, you sum them externally and connect it into the. Okay. So, however, the advantage of this is simplicity of this type of scheme. The disadvantage is that there's no built-in, for example, curve, those slope to overcome any CT situation. So it's need to be very careful during the design stage to on the fault level that you will be encountering. So here there's a certain requirements that the CT secondary current is less than 100. Basically, this is to ensure that your CT won't saturate because there's no provisions or slope to prevent any CT saturation that could cause the misoperations. The burden are less than rated, basically saying that you don't want to, when you use this type of simple differential schemes, making sure that your CT does not saturate under fault. So you need to clear and familiar with the fault level that you're dealing with. High impedance bus protection. This is very interesting, and it's the very tested and true type of protection scheme over the years. The characteristics are the CTs are parallel. You can see that parallel externally. There's a very high resistor in series with the relay coil and a varistor in parallel to prevent overvoltage. So during external fault, during internal fault, a high voltage will develop and operate the relay. A slightly lower voltage will develop for external fault. And that's how what the relay was set. You actually was set to assume a complete saturation, short circuit of the exciting branch of one CT circuit, typically the furthest one, and then plus a certain margin, and then that's basically your setting threshold. The setting is entered in volt, the operating volt. Okay, and then also you want to confirm the achievable sensitivity based on that set operating voltage. Of course, you want the relay to be as sensitive as possible, so you want to check that. So the more circuit you connected in parallel, of course, you lower your sensitivity because you require more current to operate a relay. Okay, so this is basically the equivalent circuit I drew here. So to basically here is typically you will see in any vendor's high impedance bus protection manual. These are the calculations. Basically, you assume this is the measuring branch. You measure the voltage, so you typically assume the complete short circuit of this excitation branch. So what you end up with is this voltage imposed on this RL and RCT, which is the lead resistance and the CT secondary winding resistance. These are the two key resistance that you want to take into account for that CT, so you need to know that. And then these basically are the voltage plus certain margin. that you will end up with the operating value of this of the high impedance bus protections. So the objective of the high impedance bus protection is to keep this operating voltage VR low, okay? Because you don't want to keep it too high. First of all, you keep it high is a safety risk. Also, you impose the stress on the cable as well. So one way to do that is to keep the CT secondary loop insistence low, of course. So the way to do that is, you can see from the previous slide, you measure that voltage actually across this RL and RCT, right? So if you, and here is actually the junctions where all the CT circuits are parallel. So it doesn't actually matter. It doesn't actually matter where. So the impedance from junction point to the relay is of no consequence. So a good practice is to actually parallel the CT as close to the CT as possible. Parallel the CT circuit, secondary circuit. In other words, pick the furthest CT, and you actually parallel in the junction box there. So because that you actually reduce the secondary the RL, the secondary lead resistance. Theoretically, no limitation in the number of parallel CT, but sensitivity actually reduces, as I mentioned. And you want to reduce the VR because when it's higher than the CT rated voltage, such as 400 volt for the C400 CT, you will produce error when estimating CT exciting bridge, hence resulting in inaccurate sensitivity calculation. And the primary requirement for this is CT must have the same ratios. Okay, because you are paralleling them externally, you are not able to compensate them through any of the I mentioned before, such as CTs or internal software methods. They have to have the main density ratio and magnetizing characteristics. Historically, high impedance bus protection is not able to provide supplementary protection such as overcurrent backup breaker failure. However, some relay vendors nowadays do continue to develop a high impedance bus differential algorithm in their modern IED platform with those supplementary protection features. Generally, sunsetting is a sunsetting and being phased out in place of the low impedance technology. Okay, another poll we'll be taking. What's the percentage of high impedance bus differential protection for the utility you work for? Less than 10%, 20 to 30%, or greater than 50%. Give it about 10 seconds, 15 seconds of time. Okay. So yeah, as expected, it's actually, as I mentioned, it's the sunsetting technology, but still you see that especially in older stations when the utility haven't got to the replacement project yet to replace those aging busbar protection. And typically they were actually the protective relays were also very old as well for those busbar, high impedance busbar protection. But they seems to be working all the time. In fact, the performance is pretty good. The operation speed-wise, everything is actually sometimes even better than low impedance, modern low impedance. So yes, less than 10%, 55% of the time, and actually some answer that is actually greater than 50%. So now the next section will head into the modern low impedance percentage restraint platform. Okay, and this is just the historical progressions of in Hitachi ABBs, how we develop our low impedance protection relays. Start with RADSS. These are static, and then we migrate into the numerical families. Right now, the current platform we have is 7. So we have the static, but they all based on the same principles. And then first of all, for the ABB RADSS is the analog technology. So basically everything you see here are diodes, transistors, and everything like that. And you need auxiliary CT to match CT ratio. Basically, the idea is just like any differential scheme, right? However, we divided the current into in and out. So in is the sum of all feeder instantaneous positive values. So for the currents coming in positive direction, we call it in. Current leaving, we call it out. So the differential is in minus out, right? And IDIF is typically very small for external fault, and restraint value is greater than operating. So basically, they are two torque generated. IDIF is typically large for internal faults, so V up will be greater than V rest and produce voltage across the trip relay and operate. So this is how it was realized before using static components before. And modern ways, exactly the same principle is the same. We have in and out, right? And then if we press, and then we calculate, first we sample, and then we extract the phasors, and then again that's based on the in, which is the sum, the positive values of all the current, the sum of all currents, and then we subtract the sum of all out currents, and then what we got is differential current. Basically, that's the same as you calculating the vectorial sum of all currents measured by the device. And then we have this slope setting, just like any vendor, so that the higher slope can overcome the situation of the CT saturations. We have a fixed slope of 53%. Some vendor actually allow flexibility of a set different slope. That depends on the algorithm inside, and every vendor is different. So this is basically how modern numerical differential busbar protection works typically. The same for across the board for most of them. The idea is the same. Okay. The benefits and characteristic of a numerical differential comparator, the low impedance schemes, is analog input currents are sampled and digitized. Current phasor are estimated, extracted, and then you calculate a differential current based on them. Similar operating technology to legacy differential comparator, the analog one that I introduced earlier. The secondary circuit loop is no longer a critical factor. It doesn't look at that anymore. Critical factor is time available to make the measurement, i.e. the time to saturation. There's an IEEE formula where you can calculate. So in ABB's relays, typically, or other vendor, typically you need 2 milliseconds to 3 milliseconds. You just need the CT to be stable for this 2 to 3 milliseconds, so that there's a modern algorithm that can distinguish that there is actually CT saturation coming in, and because of that, you can block the false differential currents. You only need that 2 to 3 millisecond windows for a stable, the correct CT. Numerical processing nature enable other supplementary IED features such as multiple differential zones, dynamic bus zone switching, zone interconnection, and check zone logic, CT saturation detection, open CT detection, blind zone, end zone protection, backup protection for each feeder connected, with such as 5051 overcurrents, breaker fail, and modern substation automation communication feature using with DMB3, 61850, and some vendors relays it supports 9-2 process bus technology, a mixture with conventional analog connected CTs or with 9-2 process bus sample values are possible, are supported. Band disturbance recording and security logging. Now, these are all common features for modern numerical IEDs. Next couple slides, we'll cover a little bit of low impedance presented restraint differential. So previously, what we introduced in here is the centralized, right? Centralized means you connect all the current circuit either by either by hardwire directly into the relay to the analog module, and then the analog module do this sampling, converting that to digital value as an extract phase. However, the limitation, of course, by that is the number of inputs you can support by each individual relay for those analog inputs, analog circuits, those CT circuits. There's a set limitation there. That's actually restricted, limited by the hardware. Some vendor have more, some vendor have less. However, if you have, but regardless how many you have, you cannot have more than, let's just give a number out there. For example, for three-phase, the most on the market probably is 10, 12. That's already a lot. If you have 20 feeders you want to protect, I think the only way is to go with this decentralized scheme. Decentralized means you actually have a bay unit in the field. You connected each bay unit you take care handles only one CT, three-phase CT circuit. So you connect directly in the field, and out of that, between that bay units, you can have 20, 30 bay units depending on the implementation set by the manufacturer. Then from that bay circuit through communication bus, typically is proprietary fiber optic communication. You connected that, you feed that information, those measurements directly into digital form, into a central unit. The central unit actually does all the things that we mentioned, that you calculate differential current, operate. When you operate, you send the signal back to the bay unit, and because the bay unit is in the field, it actually has a very short run to the circuit breaker to operate, to connect to the trip coil of those circuits to operate them. So this is the decentralized. It's very similar to actually 6159-2 process bus. The only difference is that this is the proprietary typically. And the other advantage actually is that these bay units actually has different protection function embedded into them, so they can additionally provide as the main two or a backup protection services right in the field, such as distance, overcurrent, breaker failure, for example, in there as a main two. So you don't require two central units, two systems. You can have, because this can be a backup scheme as well, depending on the standards of redundancy and criticality of the redundancy for that particular substation applications. In our case, ABB's case, sub-cycle performance is suitable for large, high voltage, extra high voltage substation, because only in those stations you need to have such a large number of connected circuits. It's highly scalable up to 60 in our case, and 32 busbar zones. Phase segregated, low impedance, stabilized current differential principle. In this case, it's the same as a centralized scheme. Central unit and bay unit are interconnected by fiber optic cable. Okay, so this is the decentralized scheme. So another poll we'll be taking. This is the final poll. So again, this is about exactly about the decentralized bus differential implementation that in the utility that you work for. What is the percentage that you have seen? I would expect most utility probably do not have this type of scheme implemented in their substation, but we shall see. Give it another 5, 10 seconds to give the answer. Okay, so none as expected. Actually, there is somebody answer about greater than 5%. Actually, I was a little surprised by that, but that means they probably do have, it's probably a transmission operator, so they have quite many larger substations. Okay, so I have a couple slides and we're done. Next is other type of busbar protection scheme includes the partial differential. As I mentioned briefly before, it's mainly applied into many medium voltage switchgear applications, such as in the main time main, the first on the top, bus configuration where the incoming source CT and the tie CT can be connected in the partial differential scheme to isolate the adjacent bus bar. So in other words, you can do this way, so you isolate bus A and bus B. So whatever falls on bus A, your incomer, that partial differential circuit will not detect anything other than the fault on the bus A. The advantage of that is you do not need to coordinate. The coordination effort is reduced that way. Similarly, on the second is multiple sources can be bundled together to reduce the number of relay needed to coordination effort. How the partial differential is typically applied. Last is the zone interlocking scheme, or sometimes we call it reverse blocking. Again, it's applied mainly on the medium voltage switchgear, especially when there's an arc flash protection already, dedicated arc flash protection, or the dedicated bus differential relay is not needed or couldn't be justified. This scheme still support relatively high speed for impedance. So how it goes is outgoing feeder will send a blocking signal when they detect the fault, and then the source relay typically either can be from the transformer protections or the dedicated 50 elements out of the incomer CTs. When they're receiving, you will block. If it doesn't, you detect the fault, you will wait a certain time, a set time delay, accounting for the processing and the communication time, and then you will operate in high speed clear. Because in that case, in that situation, you will believe he actually will believe that it's actually the fault on the bus. So conventionally, this was achieved by inter-relay hardwiring, right? So all the hardwiring output to input wiring. Modern implementation can be achieved with high-speed peer-to-peer communication, such as GUIs. So this typically can achieve an operation of less than 100 milliseconds plus breaker clearance time. It's a lot faster than you have to wait, coordinate. The coordinate margin is at least the inverse overcurrent coordination margin is at least 300 milliseconds. So you could save another 200 by this way. Some references. Again, the first one is NCC37, the guide for protective relay for power system buses. Welcome everybody to take a look. And the second one, of course, if you're interested, to see our portfolio of busbar protection lineup. Summary is a reliable operation of busbar protection is critical to system stability and personnel safety. Differential busbar configuration calls for different protection consideration to meet different challenges. Its most commonly used modern busbar protection scheme is low impedance right now. There's still a large install base of high impedance protection scheme, but it's gradually being phased out, and this is being supported by the poll we did today. So this is the end. Thank you. So we'll check. We'll progress into the Q&A. And then let me see if there's any questions. There's a couple questions already. So one question, can you cover 9 bay CT with 1 REB 670? If more than 1 is required and moving 3 is the only option, or can it be covered by 2? Well, this is talking about specifically about ABB's capability. So the answer is the maximum you can cover with 1 relay is 8. So more than that, unfortunately, you would need 3 boxes. 3 boxes you can cover 24 phase, single phase. What type of differential protection is used in ABB INX busbar protections? I'm not familiar with this INX busbar protections, so I can't answer these questions, but I will take a note and I will look into that. If you would send me an email, I can actually find out for you. But this sounds like a legacy. Quite a few questions here. In terms of IEC 61850, what are the most common logic nodes that are used to protect the busbar? Well, the busbar, because the nature of the protection is differential. So really, I mean, for every vendor, if in terms of their 61850 implementation, you can add prefixes to your protection. So basically, the logic node will be PDIF. So that's the name for differential. Okay, so every vendor can have different designs. Inside that logic node, you can have different. The way Hitachi Power Grid, ABB Power Grid implement this is we make that as a logic device, and under the logic device, we have multiple PDIF, because we have 2 zones, so each zone will be 1 PDIF. And also we have multiple PTRC, which is the tripping, because we have each bay is capable of tripping on its own. So each bay, each PTRC is represent each base that's capable of issuing the trip command. So that's how we implemented a logic device with multiple logic nodes under. What are the potential solutions to address the vast number of connected feeders to a bus differential zone exceeding the IED's physical analog capability? As I mentioned during my presentation, so there's always a limitation to how many analog CT circuit you can connect it to a centralized protection relay, because some vendors support more, some vendors support less. So if you have more than what you have, more than that can be offered or protected by a certain protective relays, IEDs, then you need to resort to other means. So two ways, as I mentioned. One is decentralized scheme. Typically, you can support. In our case, we can support up to 60 bays. However, you have to weigh in between, for example, the cost as well, because you need to separate bay units and the central units. Bay unit, you need one bay unit for each connected circuit, connected feeders. The other way, of course, if you can, that you have to consider how you will protect the busbar, a large busbar during that, the substation design stage. For example, you add, feeders, sectionizer to actually divide that big busbar into multiple smaller ones that you can actually protect with modern, reasonably numbers of modern relay platform that you can support. For example, up to 8 three-phase circuits, then you can probably divide that way. But this, of course, need to be factored in during that original substation layout design stage. What are some of the supplementary features to modern bus differential IEDs? So as I mentioned, the most common features, actually, modern IED platform all support these, for example, substation automation feature using supporting different communication protocols. DMP3, 61850, you support most of them nowadays support 9-2 LE for sample values, where you can reduce the number of hardwired